Hello. In addition to my two previous videos in which we studied geostationary satellites above, first of all, Earth and then the Moon, we worked out how high a geostationary satellite would have to be above Earth and above the Moon, respectively. Now, like I said in those previous two videos, a geostationary satellite is a satellite that moves about a planetary body such that it is always or always remains above the same point on that planet. It never moves away from it. This is exactly the case for a geostationary satellite above the planet Mars. As the geostationary satellite is orbiting the planet Mars, it always stays over exactly the same point on the planet. Now, what we want to do, and I might have already alluded to this already, is we want to work out the radial distance from the centre of Mars that the satellite assumes. And also, we might want to work out what the radial distance is from the surface of Mars to the point that the geostationary satellite assumes. So let's make a start. We'll draw a circle representing the planetary orbit. So we've got a satellite of mass m and it's travelling at velocity v, and that is the centre of Mars. We'll call it big M, and we assume that all the mass of the planet is concentrated at its centre, right there at that point, as shown on the diagram. Now, we've got to mark in a few other things. So, for example, the distance from the centre of Mars that the satellite assumes is big R. And if we draw in Mars's surface, it goes round something like this. Now, I know that's not a brilliant circle, but we can draw in the radius of Mars, which is R sub m. And if you remember back to the previous two videos, I had a force exerted on the satellite directly acting towards the centre of the planet. We'll draw that in. So the force acting between the satellite and the centre of Mars is F, basically. So now we can write down our equations. Now, because this is a geostationary satellite, this force component, F, has two components, but the two components are equal. So what we do is we write down the first force, and this is due to the acceleration of the planet, mv squared over r. So that's force 1. And we've also got a second force, which is big G, big M, little m, all divided by r squared. And we'll call that equation 2. So we've got equation 1 there and equation 2. Now, like I said, if I just click off that and scroll down, because we're talking about a geostationary satellite here, which always assumes the same position over the same point on the planet, we can equate these two forces, equations 1 and equation 2. So what we actually have is, if I can squeeze this on here, is mv squared divided by big R equal to G big M little m over r squared. Now, I'm going to just scroll down a little bit because I don't think I really left enough room there. But anyway, we'll leave it as it is. We'll call this equation 3. Now, you'll notice with equation 3, as scrawly as it is, that we've got two m's. We've got a small m here, which is the mass of the satellite, and the mass of the satellite m over here. And we've got two r's here, one on either side of the equation, which can be cancelled, just like the m's. So eventually, if we cancel the m's and the r's, then we get, and I'll write this down, we need to highlight it in blue, we get v squared equals g big M over r. Now, we'll call that equation 4. Okay, but like you might remember in my previous two videos, as I said there, we don't know the velocity of the satellite. If we did, we could work out straight away what big R actually is, the radius of the satellite from the centre of the planet. But what we do know is that if I just draw the satellite orbit again, now as the satellite travels for one revolution, or travels in one revolution about the planet mass m, and this is little m, in one revolution, that satellite travels a distance, we'll call it d, equal to 2 pi big R. So let's put the big R in there. It's just the circumference of the circular orbit that the satellite covers, 2 pi R. So this must mean, since velocity is distance divided by time, that v is equal to d over t, which is equal to 2 pi r over t. I'll just write it down here again because I want to label that equation as equation 4, I think. Actually, equation 5. So let's just label that as equation 5. Right? Now, if we substitute equation 5 into equation 4, now let me just scroll down because I haven't left myself very much room to write on. So if I just backtrack there and cut and paste, I think we can salvage this presentation, this lecture. Let's just put that up there, Control V, right, there we are. So if we substitute equation 5 into equation 4, we get, and I'll just write this out, substitute equation 5 into equation 4, we get 2 pi r over t all squared, and that's equal to, I have to remind myself what the equation was, is equal to gm over r. Righty-ho. Now we'll just scroll down a little bit because we can simplify this equation to get 4 pi squared r squared over t squared, and that's equal to gm over r. Now, we can simplify this equation to make r the subject. So we've got, or rather r cubed the subject first and foremost. So if we multiply, I'll write this down, multiply both sides of, shall we call this equation 6? I think that's going to be equation 6, isn't it? Yeah. Multiply both sides of equation 6 by r and t squared. We have let me just scroll down a little bit. We have 4 pi squared r cubed equal to gm t squared. And then what we do is we divide by 4 pi squared to get r cubed equal to gm t squared over 4 pi squared. Right, so we're nearly there. Now, we know what gm and t actually are. So I'm just going to see if I can cut and paste all of these constants, and we'll paste them here, Control V, but it hasn't worked, so never mind. Let me try again. Right, I don't think it's going to work, but anyway, we know that G is 6.672 times 10 to the minus 11, and T is 24.623 hours. We convert that to seconds, because all of this is in newtons, meters, kilograms and seconds and so on, so SI units. And we know what M is as well, so M, G and T. So if we substitute the latter 3 constants into equation, we'll call this equation 7, right, there we are, we get r cubed is equal to 6.672 times 10 to the minus 11. And I'm going to check that because I don't remember things very easily. So big G is 6.672 times 10 to the minus 11. M here is equal to 6.39 times 10 to the 23. So that is times 6.39 times 10 to the 23 times T, which is 88642.8. Right, 88642.8 all squared. And I want to double check that because I've forgotten straight away. 88642.8. Yeah, looks like we're on the ball this time. Divided by 4 pi squared. Now, I haven't worked this out at the moment, so I'm going to just tap this into my calculator and we'll do the calculation together. So we've got 6.672 times 10 to the power minus 11 times 6.39 times 10 to the power 23 times 88642.8 all squared. So that top line comes out to be equal to, I'll put the r cubed there again, r cubed is equal to 3.35 more or less times 10 to the 23 divided by 4 pi squared, and that comes out to be, in fact actually we'll write it underneath because I want to label the equation. Let me just erase those two. There we are. Right, so r cubed is equal to, let's do the division, divided by 4, oops, making mistakes, divided by 4 pi squared, and that comes out to be equal to, I'll do it to about 5 significant figures, so 8.4856 times 10 to the 21, and this is going to be in meters cubed. So all we have to do now is take the cube root of both sides of that equation. I should give it a name really, shouldn't I? So we'll call it 8. It's always good to identify certain things. So there we are, we'll call that equation 8. The cube root, taking the cube root of both sides of that, let me just bring that down a little bit. Right, okay. So r is equal to the cube root of 8.4856 times 10 to the 21 meters cubed. Now, I'll just write that a different way. I like to explain all my steps so that if anyone isn't sure, hopefully they will be able to understand at least one part of the method or methodology. So this is the same as writing 8.4856 times 10 to the 21 meters cubed, all to the power 1/3. And if we work that out, let me just put that into my memory, the calculator memory, but I could do with putting it into my own as well. Right, recall memory, to the power 1 divided by 3, and we find that r is equal to 2, now I have to count this, 20,396,768.35 meters. Right, so it's 20,396,768 meters. Now, I'm just going to write that in a little more condensed form because there's quite a lot of gaps in that, so many apologies. I wasn't watching the screen as I wrote it down. So that's 768.35 meters. Okay, so what's that in kilometers? Above the centre of Earth, centre of Mars, I apologise. So if we divide by 1,000, that comes out to be 20,300 396.768 kilometers above the center of Mars. I'll just write that down for you. So the satellite orbits, let me just orbits Mars at 20,396.8 kilometers above the center. Okay, and that's the center of the planet Mars. Let me just doesn't look like it's not very good writing, is it? Not very clear. So let's just put planet in there. I still can't write properly. Oh well, that will have to do. Planet. Now, how high is the satellite how high is the satellite above Mars's surface? Mars's surface. Well, for this, we'll call the height, let height equals h, where h equals r minus rm. And if you remember what r sub m actually means, it means the radius of the planet Mars. Not the radius of the satellite orbit, but the radius of Mars. So that is, we'll take the kilometre value of it, which is 3,397 kilometres. So 3,397 kilometres. So the height is, what do we get? We got 20,396.8, 20,396.8 minus, and I have to look at the figure again because I've forgotten, 3397 and so if you do simple subtraction, we get minus 3397, and that comes out to be 16,000 999.8 kilometers, and that's above the surface. Above Mars's surface. Okay, and I'm going to double check a figure I want to make sure that I did get the radius of Mars correct, and that is correct. Because the diameter of Mars is 6,794 kilometres. So the radius is half of that. So there we have it. Two values for... I can't draw straight lines very well, can I at all? It's terrible. There we are. Oops. So we've got a value of 20,396.8 kilometres above the centre of the planet for a geostationary orbit, and around 17,000 kilometres above Mars's surface for the geostationary satellite orbit. So basically there you have it. So I hope you've enjoyed that video, and you will come back and watch more of my videos. There are already a number of them out there, but I should be putting others up in future. So please do keep coming back and subscribe. And I look forward to seeing you again. So I'll say bye for now and see you soon. Okay, bye.